Hello, everyone, and welcome to another wonderful day of PChem. So today we're going to continue our conversation on mixtures by looking more at some measures of free energy. Specifically, we're going to be talking about how our good old friend, the chemical potential, actually just is another form of a molecular property, a partial molecular property. So this is actually quite analogous to what we did last time with partial molar volume, because it turns out the full definition of uh, the chemical potential can actually be given as the change in Gibbs free energy per the change in the number of moles of the given species of interest. Again, under constant pressure, temperature, and amount of other species. So another way of viewing this is just like with partial molar volumes, that the chemical potential is going to be concentration specific. So as the concentration of our species in the surroundings changes, or the concentration of species J with respect to the total composition, we're also going to be expecting the chemical potential of the system to also be changing. So what we can actually do is go ahead and integrate the system just like we did with partial molar volumes. And what we can actually get is a expression for the free energy of a system with respect to the chemical potential of A and its amount, and the chemical potential of B and its amount. So again, just like with partial molar volume, one way that we often end up thinking about the free energy of the system is essentially just a combination of the molecular of the chemical potentials of each of the individual components times the amount of that component present, or alternatively, the free energy per 1 mole of species A for the chemical potential of A. Now, this actually has some fun implications for how we can go ahead and treat changes in free energy. Because what we can do is combine this expression with what we already saw um, with what we already saw for our fundamental equations. So this gives us the fundamental equation of chemical thermodynamics, where we have our good old-fashioned free energy that we saw for a single component system, where the free energy depends on pressure and temperature. But as we've seen, as I increase the number of constituents in the present, I have to increase the number of variables that's required to describe the system. So we also see a dependence upon the chemical potential of A, and the change in the number of moles of A, and the change in the number of moles of B. So this actually is a fairly useful metric of looking at the free energy. And this really is going to be the fundamental equation that we're going to be using proceeding on, as it allows us to examine what happens to the free energy of real chemical solutions and mixtures as I change pressure, temperature, and amount of the species of interest. So again, this is quite a powerful equation. We can also use this fundamental equation to help give us other measures of how we can determine the chemical potential of a system. So one way we can do this is by combining it with some of our other thermodynamic properties. For example, we can actually relate the change in internal energy to the change in Gibbs free energy by essentially using several of our corrections that we've already presented in the previous chapters. And when we combine all these together, what we end up generating is a metric of the free energy of the internal energy of the system as negative PdV and TdS. So again, this is a familiar metric. This is exactly the fundamental equation for the internal energy. But what ends up tagging along is these expressions of the chemical potential and composition of the system. So what this ends up meaning is, say, if I want to look at the chemical potential of A, what I can do is try and fix my other three variables, the volume, the entropy, and the composition of all other components. And when we do this, one of the ways we can describe the chemical potential of any species J is how the free energy, how the internal energy changes with the amount of that species under constant volume, entropy, and the composition of the other species present. And we can actually repeat this for our other, for all three of our other thermodynamic properties, as free energy is going to show dependence on pressure, temperature, and the composition of the other species. Enthalpy on pressure, entropy, and the composition of the other species, and Helmholtz again on volume, temperature, and the composition of the other species. With again, the two other variables besides the composition of the other species being our old friends from thermodynamics, where we're describing essentially what variables the related thermodynamic properties end up holding. So this gives us a great deal of flexibility, as I may not always be able to, say, control pressure and temperature, and thus look at changes in Gibbs. I may actually be stuck in an isochloric as an isenthalpic system, or an isochoric and isothermal system instead of an isobaric one. So having these controls is actually very useful because, again, it also really shows that chemical potential can actually be quite a translatable property, as it allows for various fixed sets of conditions. We can also essentially use our free energy expressions to examine what's going to happen to our chemical potential if I start changing the composition of the mixtures. Because again, we really want to try and figure out how I can relate, say, the chemical potential I just determined on the previous side with all the other chemical potentials present in a mixture, as most mixtures are going to have at least two components. So let's go ahead and take a look at that two-component mixture. And so if so if my composition essentially changes slow enough, I can look at how the free energy of the system changes based on how the amount of moles and the chemical potential itself changes. Now, if I change my composition relatively slowly enough, I can treat my amounts of A and B as relatively constant, and thus what I'm really going to be looking at is how the chemical potential ends up changing with concentration. As we've already demonstrated that chemical potential, like molar volume, is going to exhibit a concentration dependency. So it turns out that if my system remains at equilibrium throughout a composition change, which we're already assuming when I'm looking at slow changes of composition, this is again another code word for equilibrium. So essentially, if I'm keeping the system at equilibrium, then the total free energy of the entire system isn't going to change. And really what I'm going to be seeing is that any changes in the chemical potential of A have to be matched by changes in the chemical potential of B. So I can say, if I've already determined the chemical changes in chemical potential of A through the equations on the previous slide, I can relate that to the stability, to the changes in the stability of the second species by pulling my chemical potential over to the left side and dividing both sides by the amount of B present. And then what we're going to see is that any changes in the stability of B are going to essentially be matched by changes in the stability of A. So let's say that if my the stability of A is increased, so I have a negative change in the chemical potential of A, then I'm going to have a destabilization of component B in order to keep the whole system at equilibrium. Because otherwise, I'll see some changes in the net potential of the system and I'll move away from equilibrium. Furthermore, this is also going to be matched by the fact that we're going to this is going to be mediated by the composition of the system itself. So let's say I have a large stabilization in my solute. So we're going to call A my solute. Well, that means that since A is relatively small and B is going to be relatively large if it's my solvent, I'm going to see a small destabilization in my solvent. And we're going to see the reverse. If I have a stabilization in my solute, a large destabilization in my solute, I'm going to see a small destabilization in my solvent. And again, this is all going to be mediated by the ratio of the two components. Now, one of the things I do want to point out is that, as we showed last time, the ratio of the two components is going to match fairly tightly onto measures of concentration that we addressed previously, such as molality or mole fraction. In fact, you can actually substitute in mole fraction for moles of A and B, because guess what? The total number of moles will end up canceling out. So again, this is going to be this equation is actually going to be fairly powerful, but you might not always see it in this form. Now, again, we looked at this for a two-component system, but it turns out that you can actually expand this to a multi-component system, at which point we call this the Gibbs-Duhem equation. Essentially, the idea is that for most systems, any changes in the stability of a single component aren't going to lead into any change in the stability of the entire system. The entire composition of the system will tend to stay at equilibrium. And so any stabilization of one component is going to be matched by a destabilization of at least one other component. Though again, as you can imagine, this becomes a lot messier by the time you hit 3 or 4 components, because you'll likely have one component increase, two components decrease, one increase, one decrease, and one stay the same. It's very hard to actually predict the exact numerical changes. However, one of the other useful things is, because chemical potential follows the same functional form as partial molar volume, we can actually apply Gibbs-Duhem equation to partial molar volume as well. With, again, the major assumption here being that we're going to see very minor changes in the total volume of the system as I just add small amounts of components A or B. And so what we would predict is that if I increase the amount of if the molar volume of A increases, I should see a decrease in the molar volume of B to essentially compensate. And so you can actually imagine this in a system such as if I'm adding potassium sulfate salt into water. So at the beginning, we should have the partial molar volume of water should be the partial molar volume for a pure species. And it's slowly going to decrease as it has to essentially make room for the potassium sulfate. And where for the potassium sulfate, as we see a small decrease in the molar volume of water, as each water molecule has to give up a little bit of volume for the potassium sulfate, we're going to see a big increase in the molar volume of the potassium sulfate, as each one's going to end up taking up, as each potassium sulfate is going to increasingly take up volume from those waters. Where if I have 18 waters that decrease a little, I'm going to have one potassium sulfate that increases a lot. With, again, this really illustrating this importance of the molar volume of the molar ratio in that prefactor term. Now, one of the things that I also want to make sure you pay close attention to is it looks like we're seeing relatively similar behaviors as, oh, I might see a little increase with the potassium sulfate and a relatively similar magnitude decrease in water. Well, watch out, because if I go from 0 to 0.1, water has decreased in its molar volume by 0.004. so not very much. In the meantime, potassium sulfate has increased by about a molar volume of about 6 milliliters per mole. So a huge amount, really helping illustrate the importance of that molar ratio. Similarly, one of the things I also would like to illustrate is exactly what sort of magnitude we're talking about with this molality of potassium sulfate on the x-axis, as we're going from about 0 to zero point 0.1. Well, if you go ahead and dust off your calculator and try and convert that molality of zero point 0.1 to a mole fraction, you're going to find out that this corresponds to a mole fraction of potassium sulfate of about 0.002. So in other words, I've still barely added any potassium sulfate on essentially a molar ratio, really illustrating how uneven these changes can be. With again, what we're really seeing here is that as I add in more potassium sulfate, I'm giving more ability for these potassiums to separate in the sulfate and really start hitting their stride with a structure that they actually like. And again, they're having to steal a little bit from all of the waters present around. So hopefully this kind of makes sense with how we're seeing changes in Gibbs free energy of individual components in a mixture, as well as how this reflects also on molar volume. Next time, we're going to actually look at what the effective changes are of the Gibbs free energies and chemical potentials as we actively start mixing the systems from its pure components. Till then, take care.